where we had wrapped up on Friday was we had talked about how substrates, localized substrates to be made out of N and P well material and twin well systems. So now we're going to talk about a different use for the N well layer. And that is the N well resistor. Okay. So in addition to forming the body of PMOS transistors, N wells may also be used to create resistors in CMOS integrated circuits. So if we have a rectangular chunk of material like so, where this face represents the cross-sectional area A of our material. The width of the face is W. The height of the face is the thickness T. And the length of the chunk of material will be L. We know that the resistance of this material, R, is given by rho E, the electrical resistivity of the material, multiplied by the length of the material, divided by the cross-sectional area of the material. And we're going to expand this slightly and say that the cross-sectional area is simply the product of the width and the thickness. Now, why this is important is because in a semiconductor process or a fabrication process, all of the N wells will have the same depth or thickness into the substrate, meaning that the thickness of all the resistors is a constant value. So instead of dealing with resistance, we deal with what's called a sheet resistance. So effectively, we will have R is equal to rho over T, which is going to be some constant value multiplied by a ratio that is the length over the width. And rho E over T is given a special name, R square, where R square is the sheet resistance of the material. And has units of ohms per square. So there are a couple of things to talk about here regarding the concept of sheet resistance. This unit of ohms per square is an odd unit if you're not used to it, because what it literally means is a square amount of area has a specified resistance. It does not matter whatsoever what the dimensions of that square is, okay? So if, for example, we have this 8 by 8 chunk of material. Since it is a square, it has some particular resistance. Let's just call R square for this thing X. Well, if I subdivide this into 4 smaller squares, what I will have is a 10 ohm resistor. Actually, let me do these resistors in a different color so we can see better how they're connected. A 10 ohm resistor, 10 ohm resistor, 10 ohm resistor, 10 ohm resistor, like so. So I can interpret this in 2 different ways. I could say that it's 10 in series with 10 in parallel with 10 in series with 10, which looks like 10 overall. Or I could look at it as 10 in parallel with 10 in series with 10 in parallel with 10, which also just looks like 10. It does not matter literally how you cut it, slice it, or whatever. This square chunk of material will always come out to have a resistance of 10 ohms, okay? So it doesn't matter if it's 10 microns by 10 microns or 10 millimeters by 10 millimeters. If it is a square, it has this particular resistance, okay? All right, so sheet resistance is out of the control of the CMOS designer because it is specific to the process node, okay? So for the on-semi C5 process, which is what I've based the notes and stuff in this class on, the sheet resistance of NWell, if my stylus will write, is 0.8 kiloohms per square, plus or minus 20%, depending on process variation, okay? So it's about 800 ohms per square. So if we wanted to design a 10 kilo ohm resistor, what would we need to do? Any thoughts? This isn't supposed to be a hard question.
Just change the length and the width, multiply it to 10, because that's the factor you can change.
Right, so if we wanted a 10 kilo ohm resistor made with NWell, we would need to put some number of squares in series, right? So we know that the resistance overall is the sheet resistance times the length over the width. From this, we can say that 10 kilo ohms is equal to 800 ohms per square times the length over the width, and therefore the ratio of the length over the width needs to be 10 kilo ohms over 800 ohms, comes out to be 12 and a half units, which means as long as our section of N-well is 12 and a half times as long as it is wide, we have a 10 kilo ohm resistor every single time. Okay. Now, there are certain constraints as to what these dimensions can be. And these constraints are what are known as the Moses design rules for N-wells, okay? Since I haven't uploaded the design rules yet, I'll have to write some down here for you all. But for N-wells, this all comes from section 1. So I'm going to attempt to make a table here. I'll get these posted on Moodle as soon as possible so we don't have to write this crap down after today. The Moses design rules. So these are the standard rules that are used in CMOS fabrication processes. Moses is an organization, I want to say they originated at UC Berkeley. I know it's a university in California, and effectively they serve as an intermediary between IC designers and the various foundries that operate overwhelmingly in Asia. And in order for designs to effectively work, you have to adhere to very specific design rules. These rules come about because the technology capability at each of these foundries is slightly different. So if you wanted to say, let's say that you were Texas Instruments and you wanted to outsource the actual fabrication of your device, and you were expecting to need several million units of a particular chip, that wouldn't be able to be handled by a single foundry in a reasonable amount of time. So instead, they would split the order up between multiple foundries with subtle variations in what they are able to do at each foundry. So the Moses rules effectively say, well, this is what we can do as long as we maintain these constraints. We should be able to manufacture this effectively anywhere. It's not until you get to special manufacturing needs, like incorporating MEMS devices alongside your analog integrated circuits and things like that, to where you need to have a dedicated foundry and equipment. Okay.
That sounds like you're constrained to the lowest common denominator.
Yeah, effectively, yeah, you are constrained. So like, there are lots of different foundries that support lots of different CMOS technology modes. At this point, the lowest common thing would be the onsemi C5. That is a 300 nanometer process node. So 300 nanometer is your scaling factor lambda, and since everything, for whatever reason, through Moses rules, it usually has a minimum of 2 lambda, you're actually looking at 600 nanometers or half a micron as the smallest transistor channel length that you can achieve. The next one is probably the TSMC, so Taiwan Semiconductor Manufacturing Corporation. They have a 180 nanometer process node. that a lot of people use. When this class first originated, I guess it was around 4 years ago, we designed to the TSMC 180 nanometer process node because the lead time on getting those chips actually manufactured was about 26 weeks, which is why there's the problem with the lab. We used to have the class in the fall, send everything off to be actually fabricated, and then it wouldn't get here until the spring. And so we would have the lab in the spring and we would actually analyze the chips that were created. That was the goal for the first year. And then there was a government shutdown. And because this is the designs get sent effectively from California to Asia, when the government gets shut down, the import-export checks and all that kind of stuff get shut down too. So we didn't actually get the chips in until after all of the students who designed them had graduated. Oh, it gets worse. So that was the first year. Then, so how our fabrication runs went, they were part of a academic license effectively, meaning that small batches of ICs were effectively tacked on to the end of a commercial run using that particular technology node. So we had to like wait for somebody to order something using that node so that our stuff could get tacked onto the end, and then they would dice it, encapsulate it, and all that kind of stuff for us. Well, the Taiwan Semiconductor Manufacturing Company decided that they didn't want to participate in that academic license anymore. So we had to change this class from TSMC 180 nanometers to on semiconductor 500 nanometer. And the lead time for that was 52 weeks, meaning that if we designed to it, a year later, you would get your stuff in. Then the pandemic hit. And so now, the on semiconductor stuff, which is the only one that's actually still able to be done using the academic license, now has a lead time in excess of 2 years, which means if you guys wanted to, if I actually had any intention of sending off what we designed, unless you were working on a PhD, you wouldn't, if you turned it in when you were an undergrad, you wouldn't see it before you finished your PhD. So now we just design it and don't send it off because it's just getting ridiculous. And we don't have $30,000+ every fall quarter to ship these off and see whether or not they work. So anyway, sorry for my 10-minute rant. So the first rule has to deal with the minimum width, and we're going to talk about why these things are this way. Then we have minimum spacing between wells. At different potentials or voltages. Then we have minimum spacing between wells at same potential. And then we have minimum spacing between wells of different type. And we are going to restrict the data in our table for only the SCMOS processes, which are the ones that we're actually designing towards here. So if you look at your MOSIS tables, which I will present to you, it'll typically have 3 columns. SCMOS, sub M, and deep. So SCMOS is literally scalable CMOS. And then sub M is for submicron. So this would have been like the TSMC 180 nanometer. And then there are rules for deep submicron, which are like more modern processes. So like 22 nanometer Intel type processes. Okay. So for the scalable CMOS, we have 10 lambda as the minimum width, 9 lambda as the minimum spacing between wells at different potentials, 6 lambda as the minimum spacing between wells at the same potential, and 0 lambda as the minimum spacing between wells of different type.
Is there a reason that needs to be explicit?
We're going to talk about all of those right now as to why these rules are set in place, actually. Yeah, so I will answer your question. So why is the minimum width of the well 10 lambda? Well, effectively, anything smaller than this, we can't guarantee that you're going to get the resistor ratio that you're looking for. So it's effectively saying it needs to be at least this large so that the mask alignment process can guarantee that the ratio, the resistor is going to have the correct ratio to get the resistance that you're actually looking for. So it's got a little bit of wiggle room in there, but really anything smaller than that, you run the risk of your resistor not being the size you want. And for an analog integrated circuit where so many different things depend on specific resistor ratios, you need to be able to guarantee that the resistors maybe aren't necessarily a specific size, but have a specific value as compared to something else, so that your voltage divider circuits and things like that that you're using for biasing will work and properly bias your electronics. Okay.
It just comes down to simple mechanical limitation.
Pretty much, yeah. All right, so why is the minimum spacing between wells at different potentials 9 lambda? Well, let's look at a picture here. So let's say that I have an N well here and an N well here, and this is my P-type substrate. And just for the heck of it, let's say that this is 5 volts, this is at 3 volts, and my substrate is at ground. What have I made, potentially? So this area right here is a PN junction. This area right here is a PN junction. And if this region right here is small, it will serve as a base for an NPN BJT. So if we allow those two N wells of different potentials to be too close to each other, we accidentally formulate parasitic transistors in our transistor device, which can be a bit problematic at times. There are some circuits that intentionally implement those parasitic BJTs because the CMOS process does not inherently have the capability to create a BJT, okay? In our Analog Electronics 2 course, I believe we didn't really analyze it, but we looked at a band gap reference circuit, which combined both MOSFET and BJT technologies. This is how you could utilize that, utilize a CMOS process to actually create those BJTs. In this class, we are going to look at what's called a beta multiplier circuit, which gets band gap voltage reference circuit like behavior, but can be created not so it can be created without utilizing parasitic bipolar junction transistors. Okay. So effectively, the closer that these two N wells of different potential are to each other, the more electronic interaction they have and the more it behaves like a transistor. So we typically speaking want to avoid that. The minimum spacing between wells at the same potential is really to just prevent capacitive coupling and things like that. And then the minimum spacing between wells of different type. Anybody have any thoughts of why that might be 0? Effectively, why can we abut an N well right next to a P well? So the short answer is a P well in a standard process is effectively the exact same thing as the substrate material. If we couldn't have 0 spacing, it would be impossible for us to put an N well inside the substrate. So that's why we can stack those guys right next to each other. All right. Okay, so these are our different rules. Another one that isn't mentioned here specifically for N well, because it's not specific to N well, is that typically speaking, you can't work with fractions of a scaling factor. So the ratio here that we have of 12.5 to 1 effectively for length over width would more likely have to be realized with 25/2. So 25 times 300 nanometers long divided by 2 times 300 nanometers wide would give us the size of the resistor that we want. Now that resistor could be considered large. So there are other things that we can do to minimize the footprint. So if we don't have an available run that is a certain length, but we have a little area that we could utilize, you can implement resistors as serpentine resistors. And so that would be something like this. So in a serpentine resistor, like so, and I'm going to go ahead and subdivide this up into squares so we can kind of figure out what's going on here. Everything behaves exactly like we would expect it to when adding up squares, except in the corners. So if current were flowing into this terminal and out of this terminal, our corners would experience a slightly different current density as the electrons move around that serpentine path. So typically speaking, the corner has a resistance that is about 0.6 R square times the normal square device. So if R square were equal to 1 kilo ohm per square, what would the resistance of this serpentine resistor look like? So we have actually, let's count these off this way. 1, 2, 3, 4, 5, 6, 7, 8 normal squares. Race, you're making a face. Why are you making a face? You know what? You're absolutely right. I'm just dumb. Thank you. 6 corners. Thank you for pointing that out. We have 1, 2, 3, 4, 5, 6 corners. And then we have this guy right here that I'm outlining in purple. What do you think that's going to look like? Pardon? Why do you say 500 ohms? That's exactly right. That's as hard as it needs to be. If it's half as long as a square, then it has half the resistance of the square. The other way to think about it would be 1 kilo ohm in parallel with 1 kilo ohm gives us 500 ohms. So we have 1, 2, 3 pieces that are at 500 ohms. So our total resistance is going to be 6 times 1 kilo ohm plus 6 times 600 ohms plus 3 times 500 ohms is, let's see, 6 plus 36 is 96 plus 1500 is 10,100 ohms, if I did my mental math correctly. 6 plus 36 is 9,600. 11. Yeah. So if we had knocked that guy off right there, we would have something pretty close to a 10 kilo ohm resistor, but it wouldn't be nearly as long. It just takes up a little bit of area. So in analog circuit design, where resistor values are much more important, corners actually largely get avoided. And so this is how I had you guys create your resistors in your 335 project, or 336, I can't remember which one. So effectively, you just lined up fingers. Like so. So let's say that these are all N-well resistors, and then you connected them to each other using the metal layers, where we haven't really discussed this yet, but as you can probably imagine, the resistance of the metal layer is significantly smaller than the resistance of the N-well layer because it's metal versus semiconductor material. And these metal runs don't really contribute to the overall resistance of this serpentine structure very much. All right, so how do we feel about utilizing N-well material as resistors? Everything hopefully fairly straightforward. Now we're going to talk about ostensibly parasitic diodes, but this is how N-wells also exhibit some form of capacitance. So when an N-well is formed inside a p-type substrate, the p-n junction occurs at the interface. We talked about this briefly a moment ago. when we were detailing the formation of the parasitic BJTs. But effectively, we have our P-type substrate, and then our well material, which I don't remember what color I used the other day, so I'm just arbitrarily going to use purple right here. We have, I got it backwards. Formation of a parasitic diet. Okay. In CMOS circuits, the substrate is usually tied to the lowest circuit voltage. So we usually keep the body or substrate at ground. And what that means is that if the N well has any potential whatsoever, our device is exhibiting reverse bias characteristics, and we have some depletion layer capacitance, right? So for our generic PN junction, under reverse bias conditions, we have, let's see, like so. We know that we are going to have some amount of stored negative charge on the P side of the junction and the same amount of stored positive charge on the N side of the junction in the space charge layer. And this capacitance, because we have stored on either side of the junction, varies with the amount of reverse bias voltage that is applied to our junction, where our junction capacitance, Cj, is equal to Cj naught divided by 1 minus Vd over V naught to the mth power, where Cj naught is the unbiased junction capacitance, Vd is the diode voltage, where based on the sign here, Vd would be considered the voltage applied where forward bias conditions would have a positive polarity, because we should expect that a forward bias PN junction has more capacitance than an unbiased, or excuse me, than a reverse bias PN junction. So recall just really quickly, when we move the plates further apart, the distance between the plates gets greater, which means the overall capacitance gets smaller here. Okay. V naught is the built-in voltage of the junction, typically somewhere in the ballpark of 0.7 volts for a silicon-based diode, and then M is the grading coefficient. I believe in 335, we just slapped a square root sign in the denominator and called it a day. In this class, we are going to take into account that we may not have step graded junctions because they're not particularly real. So M is 0.5 for step graded junctions. And 0.333 or 1/3 for what are called linearly graded junctions. Whereas the name implies, a linearly graded junction is one where the carrier concentration changes in a linear fashion from one side of the crystal to the other, as opposed to an abrupt shift from N-type material to P-type material.
Information for that, kind of like black marks for this.
Yes. I mean, all of that tech, where the 1/2 and 1/3 come from, or just the equation in general?
Oh, the equation in general, I remember from whatever solid state was.
Right. Yeah, so the value for M is effectively experimentally determined depending on the type of the junction. It usually works out to follow this particular pattern. Okay. Let's see, how much more math do we want to throw here? Let's just throw some other stuff in that's purely review. Just because we may need it. The unbiased junction capacitance, CJ naught, is epsilon A times Q over 2 epsilon B naught times NA ND over NA plus ND. All of this is to the 1/2 power, where epsilon is the permittivity. And so this represents ER, the relative permittivity of the material, times epsilon naught, which is the permittivity of free space. And then Q is our elementary charge, 1.602 times 10 to the negative 19 coulombs. And then finally, our built-in voltage V naught is ABT over Q times the natural log of NA ND over NI squared, where this whole thing right here is often called the thermal voltage, 26 millivolts. Ni is the intrinsic carrier concentration. Of the semiconductor. So for silicon, 1.0 1.45 times 10 to the 10 per cubic centimeter, depending on who you ask. I think I just typically use 1.0 times 10 to the 10 because that's what I learned way back forever ago when I took solid state, but it really does depend on temperature and a bunch of other things and who you ask. And finally, KB is our Boltzmann's constant, 1.381 times 10 to the negative 23. I have here the units are electron volts per Kelvin, but that can't be correct because the electron volts version of this constant is like 8.5 times 10 to the something. So this has to be joules per Kelvin. Yeah, I don't know why I have electron volts per Kelvin written there because I know that's wrong. So, and capital T here is the temperature measured in Kelvin. All right. So let's put some of this knowledge into use. And so by that, I mean specifically, let's look at an example problem here. We're not going to get too in the weeds with all the math for this. Okay. So we're going to be looking specifically here at the capacitance that's formed by an N well. One of the things that we did in 335 and 336 when we looked at these capacitances was we treated our PN junctions as if we had a chunk of N-type material and a chunk of P-type material, and then we fused them together where the junction was just a nice, easy line between the two things. We know, based on what we've been looking at, that in truth, our junction is going to have a pretty different look to it, right? So if we have N well here and P-type substrate here, what we're going to find is that we have some bottom capacitance and a sidewall capacitance effectively around the perimeter. Okay. All right. So our goal here is to determine the depletion capacitance of an N well P substrate diode with dimensions of 100 lambda by 100 lambda, where lambda is equal to 300 nanometers for our process. Given that, the substrate doping is 10 to the 16 dopants per centimeter cubed. And the well doping is 10 to the 17 per centimeter cubed. The measured stylus is being difficult, sorry. Zero bias depletion capacitance of the junction is 100 attofarads per micron squared. Sorry, my thing keeps jumping on me. And the grading coefficient is M equal to 1/3. Assume the depth of the well is 3 microns. And then finally, I'm going to have to look somewhere else in this problem statement because I don't see where I mention a voltage, but it obviously has a voltage. Otherwise, this whole thing would be looking like zero bias. So the grading coefficient would not matter. Assume the depth of the well is 3 micron and nope, I don't specify it, so I just find the junction capacitance as a function of the diode voltage. So let's just leave it at that then. Okay, sorry. All right, so let's talk our way through some things here, okay? Effectively, we have, Neil, what's up? An attofarad is 10 to the negative 18 farads, yes. Yes, -9 nano, atto a billion times smaller, yes. All right, so we mentioned what was happening briefly when I drew this kind of picture here, but effectively we have a box, right? The bottom of the box forms some capacitance, and then the perimeter of the box also forms a capacitance because all of that surface exists as a PN junction, right? So we're going to break this thing into two different parts. We are going to find the unbiased junction capacitance of the bottom. We're going to find the unbiased junction capacitance of our sidewall, and we're going to add these two terms up, and then we can treat it as a simple capacitance that varies with voltage, okay? So for the bottom, we're going to have CJ0 B, which is our unbiased junction capacitance for the bottom, is going to be ZJ0. So this is one thing also that I want to point out. So typically speaking, the junction capacitances and things like that that are given in the CMOS process are per unit area. So they're also kind of a capacitance per unit square. That being said, the dimensions of the square absolutely matter for a capacitor, because capacitance is all about area of overlap, right? So it's not just the shape of the geometry that is important, it is the actual physical dimensions of it as well, okay? So then we're going to multiply this by the bottom area. And then we're going to multiply this by our scaling factor squared, where the bottom area times our scaling factor squared is actually going to give us the physical dimensions of that particular capacitor, okay? So for us, this is going to look like 100 times 10 to the negative 18 farads per micron squared. And then our well has a bottom area of 100 times 100. And then we have a lambda times a lambda as well, where lambda, 300 nanometers, is 0.3 microns squared. And hopefully we can see here how the units will work out to give us just a particular value of capacitance, right? So if we throw numbers in here, we wind up getting 90 femtofarads. So based on how we figured out what this bottom capacitance is, I want you guys to tell me how you think we might solve for the sidewall capacitance. How are we going to get the total surface area of the sidewall? Yeah. Okay, so the area of the sides and add them all together, okay? So I would argue that it's just the perimeter times the thickness. One way to do it, right? Okay. So for our sidewall capacitance, I'm asking you to think about that so that when I give you a problem and I ask you to do it, or I'm not there to tell you what it is, you'll think about, oh, this is how you do it. Anyway, so for our sidewall, we're going to have CJ naught S is equal to CJ naught times our well perimeter times our well depth so this is going to look like 100 times 10 to the negative 18 farads per micron squared. Our well perimeter, what's that going to be? Not a trick question. We have a square that's 100 by 100. What's the perimeter? 400. So 400 times our scaling factor. So that's going to be 0.3 microns times the depth of our well, which is 3 microns. And this comes out to be 36 femtofarad, right? So for this particular example, the sidewall capacitance is comparable in scale to the bottom plate capacitance. Obviously, if you make a capacitor that has a larger bottom plate area, that's the one that's going to be dominant, but this is small enough to where we can see that there's actually, we would need to include the sidewall parts to have a better idea of how this is actually going to behave. So just something to be careful about. All right, so while we're at it, let's calculate our built-in voltage, which I'm calling V naught because that's what I used in 335. So this is our thermal voltage times the natural log of NA ND over Ni squared. Since we're dealing with silicon, 26 millivolts for our thermal voltage times the natural log of 10 to the 16 per cubic centimeter, bless you, 10 to the 17 per cubic centimeter. And it looks like when I made out these notes, I was using 1.45 times 10 to the 10 per cubic centimeter as the intrinsic carrier concentration of silicon. So we're just going to stick with that because I didn't bring a calculator downstairs. We get 759 millivolts as the built-in voltage, which seems pretty reasonable for a silicon-based device. From here, then, our biased junction capacitance as a function of the diode voltage VD is going to look like CJ naught B plus CJ naught S, all divided by 1 minus VD over V naught to the mth power, or 126 femtofarads over 1 minus VD over 0.759 volts to the 1/3 power. All right. So we still haven't finished all of our NWEL notes. We're getting very close though. We only have 2.5 minutes left of class, so this is where we're going to stop for the day. What we're going to talk about in the next class meeting is a combination of these two things. We have observed that our NWEL material, when we have excuse me, our N well material inherently behaves like a resistor. If we apply a voltage to our N well material, it also exhibits some sort of capacitance. So what do you think happens when we have a section of material that exhibits both a resistance and a capacitance? It introduces delay into our signal because it forms an RC ladder network. So we are going to talk about what kind of delays arise when using N-well as a resistor material when it's got a voltage applied to it. And that'll finish up our discussion of N-well type things. And then we are going to move along to, looks like I have metal layers next. Based on the chapters of the textbook, we might swap that around to talk about the active regions actually, since that's our next hierarchical step in the formation of our inverter. So I will see you guys, I'll see actually the overwhelming majority of you in 15 minutes in the IESB. And I'll 108. Yeah. Yes. So for senior design. Yeah. And then I'll see the handful of others on Wednesday. Neil, what's up?
What was the textbook?
It'll be on the syllabus, which I have yet to put up. Something like CMOS Integrated Circuits by R. Jake Baker. I know who the author is. Jacob Baker. I think it's R. Jacob Baker. I'm using the 4th edition for what it's worth. Just because I have it. I know that the 3rd edition, or let me say this better. I've heard that the 3rd edition can be found online for free. I would know nothing about that though. Yeah. Word on the street is you can find it if you look for it.
So on the CG